Okay, I think otherwise it's okay. The program for the next couple of days is as advertised. Okay, so I want to just briefly remind you of these various results. Even though I finished with a list of theorems, I will just put some summary, some short version of this, just to remind us of where we are. So we have a theorem 1 that basically says that it's lambda is a hyperbolic set, non-uniformly hyperbolic, so non-zero Lyapunov exponents, and gamma in lambda is a sufficiently small, nice, almost recurrent rectangle. And then it implies that it is hyperbolically almost recurrent. So this means that it has this property. Unfortunately, this is dry very much. It's drying very slowly. Okay, so we have a rectangle, and we have a point X that has a local stable manifold, and at some point this point X comes back inside. So this should be also, yes, nice. So we have these two periodic points P and Q. We use all these properties. This is the stable manifold P, unstable manifold, stable manifold. So the point X comes back at some point, Fi of X, and it has an almost return, which means that if you look at the image of its local unstable manifold, or its local stable manifold, then it intersects some manifolds. Okay, so this is just an almost return. So every time you have an almost return, then what you actually have is a very strong structure, which is that you have a stable strip here that maps hyperbolically, so it shrinks in this direction, the stable direction, and it stretches in this direction, and it maps exactly to some unstable strip here with some uniform hyperbolic estimates that are not specified, but it just has some uniform estimates. Okay. So this is a fairly strong property. And then theorem 2 said that if you have this property, so gamma is nice and hyperbolically almost recurrent, then so sorry, it's more useful to call this gamma 0 because we're going to move on to another gamma. So if we have gamma 0 that is hyperbolically almost recurrent, so here we remove, we do not need to be inside a hyperbolic set. We now are kind of self-contained. We just have a rectangle that is nice, hyperbolically almost recurrent. And then this implies that there exists another rectangle, gamma, which contains gamma naught, which is nice, hyperbolically recurrent, so this means that in fact every point actually has infinitely many actual returns to the point of the Cantor set of the rectangle, and every time you have such a return, you also have this hyperbolic branch, and also saturated. So I will recall in a second what the saturated condition is, because that will be very important. But this is a construction. The aim of this step is precisely to get this saturated condition, which is a priori not at all trivial. And then theorem 3 says that if you have this, so if you have gamma is nice, hyperbolically saturated, hyperbolically recurrent, and saturated. This implies that gamma supports a first return topological Young power. Which I have not yet defined, but which I will define now. So in fact, today I'm going to prove this theorem here. I'm going to define the topological Young power and prove this theorem, which is I think one of the most interesting parts of the argument, because it is not at all obvious that these straightforward conditions implies this. And the final two theorems were more kind of moreover in some sense, so, but I will state them just to remember to be clear. So this first return topological Young tower, moreover, if gamma is fat, so moreover, as in if gamma is a nice hyperbolic that can saturate a rectangle. Moreover, if gamma is fat, in the sense that the union of the local stable manifolds has positive Lebesgue measure, then this implies that there exists SRB measure. But it might be infinite, okay? And often we're interested in these SRB measures being probability measures, being finite, and so moreover.
But infinity, it's sigma finite.
Sigma finite measure, yes, because when you have the tower, you have an induced map, so you have a finite SRB probability measure for the return map, and then you need to spread it out. And if the return times are not integrable, when you spread it out, you end up with an infinite mass. I will mention that a little bit, okay? If you're not, I just mentioned this for people who are familiar with this construction, but you always get it sigma finite because it is just a finite measure that is spread out by the dynamics. I will give that definition. Anyway, it's a sigma finite measure. Moreover, if gamma belongs, this is the only place where we come back to the hyperbolic set. So I should say, okay, I did not specify that, but if you are in this setting, then gamma contains gamma 0 and is still contained in a hyperbolic set. Okay, this is kind of implicit. But if gamma is in the hyperbolic set, then this implies that there exists SRB probability measure. There exists SRB. So this is the full structure of the proof that if you have a hyperbolic set, and if you have gamma 0, which is a sufficiently small, nice, almost recurrent rectangle, then you have an SRB measure, SRB probability measure of the sequence of results. So let me make one comment again about the different strategies and techniques for constructing SRD measure. In some sense, the kind of argument that Dyasha Pesin was talking about just earlier this morning still needs to be applied. So you still need, in this part here, once you have the Young tower, you still need an argument to construct the SRD measure. And essentially this argument still involves, whichever way, one way or another, you always have to kind of push forward some measure and construct these sequences of measurements so that they converge to an SRD measure, right? So one of the differences is that in this case, it's fairly easy to do that because here you have a Young tower which has a very special structure. In some sense, you have a return map that is uniformly hyperbolic, so you can do it. And so you do it once and for all. And then the strategy is, okay, we've already shown that when you have a Young tower with certain properties, then you have an SRD measure, and then you don't have to worry about that anymore. And then you change the problem, and you say, okay, my problem now is a geometric problem of constructing Young towers in specific situations. So you can either take that approach, and you say, okay, I've got a specific situation, I'm going to construct the Young tower, and then I get the SRD measure essentially for free because that has already been proved. Or you can do what Pesin is going to talk about, which is take a specific situation and then do the actual construction, do the whole argument in that specific situation and take into account the specifics of the map you're considering. So in both cases, you still need to take into account the specifics because in our case, to construct the Young tower, you need to somehow take into account the specifics of the situation. So just to give you an idea of how these various approaches fit together. So so what I hope to do between today and tomorrow is hopefully to prove these two theorems. As I said, these ones are fairly standard. These two are just require showing that this Young tower satisfies some distortion estimates and then applying general results of Lysen-Young that show that you have SRD measure in this case. This one is really highly technically non-trivial, and it uses the theory of systems with non-uniform, with non-zero Lyapunov exponents to some extent, even though still is not so difficult. And these ones are kind of self-contained, and I think they're very nice arguments. So this is what we'll do. So today I want to start with theorem 3, and I hope to be able to prove essentially pretty much a complete proof. Yes?
Just a question. Here you don't assume that delta is an attractor.
Yes. Yes, I assume, I'm sorry, yes. So I assume it here when I say that it's fat because, so I'm not assuming that it's a topological attractor in the sense that Pesin wrote, in the sense that it attracts a neighborhood. But I'm assuming that the family of stable leaves has positive Lebesgue measure. That's what I mean by fat. And that essentially means it's an attractor because it means there's a positive Lebesgue measure set of points that converges to whatever set, to the set we're considering. But you're right, sorry. So here, none of these three theorems require it to be an attractor, but the main theorem is actually if lambda is a hyperbolic set and gamma 0 is a sufficiently small, nice, almost recurrent, fat rectangle, then there exists an SRD measure. Yes, thank you. So the actual main theorem includes the fatness assumption. Yes?
And I want another, what was hyperbolically almost recurrent?
Hyperbolic almost recurrent is just this. So almost recurrent means that every point has an almost return, which means it returns in this way. And hyperbolically means that every time you have an almost return, you have a hyperbolic branch associated to it. So the existence of this hyperbolic branch is, of course, non-trivial because it's much more than just having an almost return. Yes. Thank you. Okay, so our assumptions now for theorem 3 are that we have a nice hyperbolically recurrent rectangle, so it means that every point has real returns. So real returns, of course, are just special cases of almost returns, but have real returns, and every time you have a real return, you have a hyperbolic branch, and that it's saturated. So I will recall in a second what the saturated condition means, but let me first give the definition of a topological Young tower. So the definition is fairly easy. So first of all, we need to define, so let gamma be a rectangle. Okay, so remember we write gamma CS and CU are just the stable and unstable leaves that define this rectangle. And then rectangles have some special structure of special subsets. So definition, we say that gamma S is an S subset of gamma if X in gamma S implies VSX intersection gamma also belongs to gamma S. So this just means that you cannot have, for example, a single point here is not an S subset. It says that if this point belongs to your S subset, then all the other points on the stable leaves must also belong to your S subset. Okay, so it's a natural definition. It's like saying you take subsets which are kind of unions of stable leaves intersected your gammas. Okay, so they're in some sense saturated in the S direction. And similarly, U subsets, gamma U is the U subset of gamma X in gamma U implies the U of X intersection gamma.
So this notation, so he has some X, does it mean that this set fully crosses the whole rectangle?
Yes, the notation I use VUX is I take the precisely this piece of the local stable and unstable manifold, right? So every time I will write VUX or VSX, I refer not to the full local stable and unstable manifolds, but just to this piece. In general, the local stable and unstable manifolds will be bigger. We have points, most of these points here will have stable and unstable manifolds which are at least of this size, but for simplicity I just refer to VUX and VSX as exactly this leaf and the whole leaf. So when I say VSX intersected gamma, I mean the whole of VSX. Okay. That was your question? Yes. So the importance of these will be clear in a second, but now I can define topological first return Young tower. So first I let tau be the first return time. Tau of x equals the first return time of x to gamma in future time. And so every point has such a first return time because assuming gamma is recurrent. And let me use this notation here, and tau is equal to the set of all first return times, set of all return of all return times, of all first return times. So definition. Gamma, rectangle gamma, supports the first return topological Young powers. If for all I in n tau, so for all return times, for all first return times, the sets, which I'm going to define like this, gamma s I, which is by definition all the set of points x in gamma such that tau of x equals I. Okay, so just the set of points that return at time I. And gamma mu I, which is by definition just the image of this set, are S subsets and U subsets of gamma, respectively. So this is saying that all the points on a stable leaf all come back at exactly the same time, basically. Rectangle gamma. This is a definition. No, the definition of topological Young tower, or first return topological Young tower. So let me motivate these words. So a Young tower. So the word topological is there because this only describes the topological structure of the Young tower. So a Young tower is a structure that has been kind of defined by Lyson Young in a few papers and to use to construct SRB measures. And what we usually refer to a Young tower is a rectangle which has a certain topological structure and certain hyperbolicity estimate and certain distortion estimates. Okay? The topological aspect of it is described here, except for the fact that in a more general setting it is not required to be the first return time. So if you replace in this definition just the fact that there exists a return time, there exists a return time function, so you could replace this, the fact that tau is the first return time, by saying, okay, there exists some return time function. So there exists a function that for each x gives some return time, not necessarily the first, that supports this property. Then this is the topological description of a Young tower. This is the structure that a Young tower has to have. In this case, I call it first return Young tower because it is given by the first return time. So it's a much stronger. Usually, you have to work a lot to get this property because there's no reason why it's possible, for example, that all these points x that lie on one stable leaf if you look at one of them and you look at its first return time, all the other points do not come back at the same time. But if you wait long enough, at some point you're lucky and they all come back at the same time. This is the general idea. Okay? It's very difficult in general. In fact, there is a version of a Young tower for non-invertible maps in which you actually have open sets, and these sets are open sets and they come back after a certain amount of time. One of the difficulties here is that, as I've explained, these are Cantor sets we're talking about, right? So we have not just the leaf coming back to the leaf. If you had an Azov diffeomorphism, right? It's much more, so this, all these definitions work very well also in the Azov case that is very familiar. In the Azov case it's much simpler because you have every point belongs to a long stable and unstable leaves. Like the whole domain here is completely filled. We have a foliation of stable and unstable leaves. And therefore in that case, a lot of these things simplify, and in particular, the hyperbolic branch gives you exactly that structure, right? So this hyperbolic branch, this stable strip, which is a union of stable leaves, which maps to an unstable strip, gives you already exactly that. If this is the first return time, okay, which you can arrange to do that, then this is already that, okay? Because you have all the points here on the stable leaf, they come back all at the same time to the other stable leaves. So if you think of the Azov setting, then all these definitions, you know, it's particularly simple cases of all these definitions. The difficulty here is that because it's not an Azov case, we have a Cantor set, and therefore, as we shall see in the construction, it's much trickier because there's lots of gaps, there's lots of holes, things can fall in the holes, and you need to match everything up. So this construction has been done for specific cases, like the Henon map in certain cases by Benedicts and Young, and for some billiard maps, I think by Chernov and other people, I'm not exactly sure. But there's only very few, couple of cases, maybe a couple of settings where you can take a system and actually construct this structure because it is a very delicate construction. So part of the motivation here is to actually give an abstract theorem that says that you only need a kind of to verify a condition like that, and then you automatically have your topological construction. Okay, so So how are we going to construct a Young tower? So recall that since by assumption gamma is hyperbolically recurrent, then we have the list, the set C of all the hyperbolic branches that come from the returns, right? So if you remember, we have all the hyperbolic branches, which we denote by this, ij, C hat, ij belongs to some index set I. So for every I, there is a finite number of possible branches. So here I is an index set where I belongs to n tau. Well, I is a return time. Okay, not just the first return time. I is a return time. And J is between 1 and some ki, which is a finite set of hyperbolic branches that have the same return time I. And we have the saturation condition. So by the assumptions of the theorem which I raised, gamma is hyperbolically recurrent and saturated. So we have three conditions. It's a nice rectangle, it's hyperbolically recurrent, and it's saturated. So the saturation condition says that F minus I of C hat U I J intersection CS belongs to CS. I will discuss this again. And this. F minus I of C hat S J intersection of C U intersection CS belongs to CS, and Fi of C hat S J intersection C U belongs to C. So what this says, remember I discussed this a lot. This is a very important property, and will be the key part of the theorem that we will talk about tomorrow will be to show that it's possible to construct a rectangle. Yeah. So now you've got this hyperbolic branch. It comes from an almost return. And now you look independently of where it comes from. Now you forget where it comes from. You've got your hyperbolic branches. Okay? And you say it's saturated if the following property holds. You look at so CS is the family of the stable leaves that define the rectangle. So you look at these stable leaves, you look at the intersection of these stable leaves. Yeah? Okay. So you look at all these pieces here, that's this, C hat U I J is this. This is C hat U I J. This here is C hat S I J. They map to each other under time I. So if you take these pieces of stable manifolds and you look at its pre-image, of course the pre-image of this goes from top to bottom. It joins these two vertical boundaries. These two vertical boundaries, they come from the vertical boundaries here. So the pre-image of this will be a long strip. Because of the uniform hyperbolicity, it will not have any strange geometry. It will just be a fairly essentially vertical strip here. And then you ask yourself the question, okay, was that strip part of my original collection of stable leaves? Okay? And the saturation condition says yes, it was in there. So by doing this procedure for all possible hyperbolic branches, you do not get any new leaves that were not there to begin with. So you had, it's a way of saying that you had a really pretty much a complete, a maximal, you've chosen all the leaves you want. Okay, so this will be very important, this set in fact. So I will use some notation for this set of leaves. So let's call this CSIJ, and let's call this CUIJ. And I want to just make a remark. Notice that, so obviously CSIJ is contained in C hat SIJ, right? So C hat SIJ is the domain, is the whole strip. CSIJ is the pullback of these strips. So CSIJ is a union of stable leaves inside this domain. Okay? So CSIJ, but okay, so in particular it belongs to C hat SIJ intersection CS. Because it's a union of stable leaves in there. But in general, it is not equal to this. And this is a very important I just want to take a couple of minutes for you to appreciate that. What the statement says is that if you pull back all these stable leaves, all the leaves that you get here, they already existed in the initial collection. But there may be some other leaves here that are not given by this pullback. Okay, we're not claiming that. It's strictly contained. We will come back to this several times, so if you not fully see it here, but formally it's quite clear. This is just claiming you have the original collection, so inside C hat Sij there's lots of stable leaves, okay? There's a whole collection, there's a counter set of stable leaves. You're saying all the ones that I pull back, they belong to this collection, but nothing stops me. In fact, in general, there will be lots of others that are not, do not come from that, okay? What does that mean? So suppose, what does that mean about their images? What this means is that here, if you have a stable leaf that does not come from this pullback, what does that mean about the image of this stable leaf? The image of the stable leaf falls, it might even be this very one that is given for the, even the one corresponding to x, might be even this one corresponding to x, which comes back here. It has it defines an almost return, but it might be that this almost return does not come back to a stable leaf. It's okay, it's not a problem. This falls in a gap of the Cantor set. So there may be many leaves which fall in a gap of the Cantor set, and they will have a return at a later stage. So because they fall in a gap, I is not a return. Well, okay, it's an almost return, but it's not. They may fall in a gap. So there may be lots of leaves that fall in gaps. Okay, that's what this observation says. Okay. So now what I want to do is I have the CSIJ, and now I want to define gamma Sij, which is simply equal to CSIJ intersection gamma. So what is this object here? This is gamma Uij, which is just Cuij intersection gamma. Okay, so CSIJ is a union of stable leaves, and gamma Sij is just the actual points of gamma that lie on those stable leaves. Okay, and then we define gamma S is just equal to the union over all x over all ij of gamma Sij, and gamma U is equal to the union over all ij of gamma U ij. Okay, so I know there's quite a bit of notation, but it's not actually as complicated as it seems. So we have 3 levels. Okay, we have, for each ij, we have gamma Sij, which is contained in CSIJ, which is contained in C hat Sij. Okay, and they're simply, this is just the actual solid strip, okay, with the hats as the solid strip at time ij. This is the union of stable leaves, which is not, and this is crucial, is not just the union of all stable leaves inside the strip, but is the ones that you get by pulling back. Okay, this is crucial. And this is simply the intersection, this is simply the intersection with gamma of these stable leaves. Okay? So this here is a domain, let's say. This here is a family of curves. Family of curves. And this here is a counter set. So interrupt me if you lose track of the notation or if something's confusing. Okay, so the first lemma. Okay, I've introduced all the notation I think I need to introduce. So now we can start proving things. And it turns out that these are exactly good. So for all ij I, gamma s ij and gamma u ij are S subsets and U subsets respectively of gamma, and moreover Fi of gamma S ij is equal to gamma U ij, and gamma is actually equal to gamma S is equal to gamma U. So this is, the proof is actually all, I will light out the proof, but it's really just by definition almost. But it's still remarkable that we've constructed these gamma Sij and gamma Uij in some sense defined a little bit independently of each other, so it's not completely obvious, immediately obvious that you have, that they're actually images of each other. This is a good part of the way towards a Young tower because these are S subsets and U subsets, which is what we want from the Young tower. They map to each other, so we have images of S subsets that map to U subset. The main thing that is missing is that we have no information about whether they're disjoint or if it's the first return time. Right? So we have some basic objects which are the candidates for our level sets that define the Young tower. So once we prove this, we'll have to look a little bit more closely. These in general are of course not disjoint. They are lots, they overlap a lot because this is all possible return times that you get here. So we will need to disentangle them and show that we can find a sub-collection of these that exactly define the sets of our Young tower. That's how we're going to do it. So we can find a sub-collection of pieces that are all disjoint and form the level. That's the second step. So there's kind of two steps in the proof. This one, and then to choose some of these that will work. Okay, so let me try to sketch the proof of this. So first of all, it's fairly clear that there's subsets of gamma, right? So gamma Sij is, as I just wrote, is a subset of, so gamma Sij is by definition C hat Sij intersection Cu, gamma Sij, yes, gamma Sij, CSij intersection gamma, which is the same thing. I mean, actually I wrote gamma, but maybe it's the same thing. Maybe it's, what I'm going to use is a little bit more that it's the CS, but it's the same thing because CSij is a collection of stable leaves. So when I say intersected gamma, it's the same thing as saying all the points of gamma are those where you have some unstable leaf intersecting, and this is the union of all unstable leaves. So actually this is the notation that I want to use. So it's contained in this, and CSij intersection Cu, and this is CSij by the saturation assumption is included in S. So this is included in CS intersection CU, right, which is equal to gamma. And in the same way, gamma U is containing gamma, so they're subsets of gamma. The fact that they're S subsets and U subsets is also fairly clear from the definition, right? Because Sij is a union of stable leaves. Stable leaves, right? And then you can immediately see from the definition, so Csij is a union of stable leaves. You intersect it with all the unstable leaves, so clearly this is an S subset, right? Because if you take any point on one of the stable leaves, then gamma Sij will contain also all the other points that of gamma that belong to the stable leaf, union of stable leaves. So gamma Sij is an S subset, okay? And similarly for the U subset is the same. So the fact that these are actually subsets of gamma and this S and U subsets is almost immediate. So then we want to show that that they map to each other. Okay, so let's see if they map to each other. So let's take Fi. Let me give myself a little bit more space here. So Fi of gamma Sij is equal to Fi, so let's put in the definition of gamma Sij in here. So gamma Sij is Cs Ij, Fi of Cs Ij intersection Cu. Okay, and what's the definition of Cs Ij is there? So this is equal to Fi of F minus I of C hat U Ij intersection Cs intersection Cu. Okay, and then you just, so this is all diffeomorphisms, so everything is bijective, so you just get here write it. So Fi, so I'm going to write this as Fi okay, so I'm going to write this F minus I, I'm going to take the Fi inside this intersection, F minus I, and I have F minus I of C hat Uij is just C hat Sij, right? Because this is the unstable strip, and F minus I brings it back to the stable strip. So I get Fi of the stable strip here, right? And then here, I just take F minus I of Cs, and Fi of Cs, they cancel out, so I just get Cs here. These are just inverses of each other. And then I get Fi, this Fi of Cu here, Fi of Cu. Okay. And then here I combine them by saying that this is the same as, what do I have? Yeah, so this is Fi of C hat Sij intersection Fi of Cu. So I write this as Fi of C hat Sij Ij intersection Cu, okay, intersection Cs. And this is exactly the definition of C hat Cuij, and then you intersect it with Cs, and you get exactly gamma Uij. Okay, so this is really just combinatorial calculation of the definitions. So notice that we have used the saturation assumption to get this, the fact that everything is included. Okay, so it remains to show that gamma S and gamma U contain everything. This is fairly clear. Let me just skip this part, okay? It's just a similar kind of calculation. You can check that it's kind of clear because every point has a return, every point belongs to some CSIJ, so every point belongs to some gamma Sij, and so so the union of, so gamma S is equal to gamma U is equal to everything. Okay, so let me skip that, it's, so we can move on. The second part, so the second lemma, as I said, so now we assume that we have these sets, gamma Sij, that are S subsets, but they all overlap in strange ways. So this is the second fundamental lemma, and then before proving it, I'll show you how they apply it here. So let KL belong to I, and suppose there exists some x in gamma S KL and some I less than K such that Fi of x belongs to gamma. So in other words, we're trying to identify the first returns, right? So we're saying, okay, take some KL, take some gamma SKL, take a point. Then we know that this point will return at time K by definition. Okay, we have this property, all these points, these are S subsets, the images are U subsets, they all return. So all these points they return at time K, but K may not be the first return time. Okay? So suppose there exists another time set that K returns before K. So that Fi of x is in gamma. Okay, then there exists some Ij in I such that gamma KL is contained in gamma, so gamma SKL is contained in gamma Sij. So as we discuss this, it will become a little bit clearer. This is a nestedness, a crucial nestedness property, which will allow us to prove the theorem. Let me say here in particular. All sets of the form gamma Sij for Ij in I are either nested or disjoint. Because what we're saying is that if two of these intersect non-trivially, then we have this situation exactly, right? So if they intersect, that means there's a point that has a return to gamma both at time I and at time K. Okay? And then we know that the one that has the smallest return actually contains the biggest one. So they're either nested or disjoint. But this is a stronger statement. This is a more explicit and stronger statement than just saying that nest or disjoint. We need both these statements. We need this one also particularly, the fact that those particular ones are nested. So let me complete the proof of the theorem with these two lemmas, and then we will prove this lemma, because the proof of the theorem is quite easy now. and helps to see what the structure is. So proof of theorem. So we need to prove that we have a Young tower. So we need to prove that the first determined time map gives a kind of level sets that are S subsets and U subsets. And it turns out that they would be given exactly by sets of this form. So by lemma 2, the set of all gamma Sij are partially ordered by inclusion. Because we just said they're all either disjoint or they're included in each other. And therefore, we can take a maximal set. So when you have a partial order by inclusion, you can take a maximal set. So you can take the set of all these elements that are not contained in any other element. Okay? This is just standard. So we can take a subset, so let I star included in I, in the set of indices, in the set of indices of the maximal elements of this partial order. Okay, then yes. Right, so remember we have gamma Sij belongs to C Sij belongs to C hat Sij, right? So the order, this is the keep in mind there's only these three kinds of strips, right? This is the full strip, okay? This is the set of stable leaves, but not all stable leaves that are in here, just the ones that you get by pulling back. Right? And this is the intersection of all these leaves with the unstable leaves, so it gives a Cantor set. Okay? This is the set that belongs to gamma. These do not belong to gamma, right? This is a full domain, that's the set of stable leaves, they do not belong to gamma. Gamma is just a Cantor set. Right? So in the end we will get a kind of partition of gamma by sets of this form. Not of this form or this form. These are just ways in which we use to define these gamma Sij. Okay? So now we are really looking with proof lemma 1 that says that in fact these gamma Sijs, they have this remarkable property. So not only are they S subsets in the set, but that is kind of obvious from the construction that S subsets, but their images are U subsets. So it means if you take one gamma Sij, so this point is something that there's only so much that I can really explain to you. You need to lie down and try to digest this, okay? Because so let me maybe try to help a little bit, okay, with just 1 minute. If you remember, I said that the key point of the S subset is that all of these points on the stable leaf, they all come back at the same time, okay? Now, however, you want a whole collection of stable leaves that has this property. So CSIJ has this property that all the stable leaves, they come back at the same time, okay? And all these points on these stable leaves, they all come back at the same time. And what that means is this is a symmetric relationship. So because not only they come back at the same time, but their image is a U subset. Okay, what does U subset mean? U subset means that if this point belongs to the U subset, then all the points on this unstable leaf belong to the U subset. So this is kind of saying that it's onto. It's a surjectivity assumption. It's a surjectivity condition. Right? It's saying that all these points that you choose here, they map surjectively onto the points of this Cantor set of these stable leaves. Yeah. That's what a U subset is. Okay. Yes.
The index R is important, but then J shows the multiplicity.
Yes, yes. J is not important. In fact, in the definition of the Young tower that I gave, I put together, I did not make that distinction. So in the definition of Young tower, I said take all the points that have certain return time I, they're an S subset. So that's a good observation. I mean, so here I'm distinguishing J's because I'm constructing these sets with these hyperbolic branches. But what I'm going to do for the Young tower, I put together all the, of course, if you have gamma Sij and gamma Sij prime with the same I, you can put them together, and both of them, the union of them is also an S subset, and their image is the union of two U subsets, which is also U subset. So the union of S subsets is a U subset and S subset. Okay, so using these two lemmas, I have this partial order, which means that I can choose maximal elements that are not contained in any other element. Right? And if I take any other one, either it's disjoint or it's included. Okay? And I claim that this is this is good for me, so I've lost my sheet. Sorry. Did I put my sheet somewhere? Here. Okay, so now we let we just take all these maximal elements. Okay, so we let P be gamma Sij, Ij now star. Okay, so we just take the maximum elements. Okay, so we would like to show that these cover all of gamma. Right? So that's by lemma 2, by lemma 1. Each by the part of the proof actually that I kind of skipped, by the fact that gamma is equal to gamma S and equal to gamma U, then every point belongs to gamma S and therefore belongs to some of these gamma Sij. By lemma 1, every x in gamma belongs to some gamma Sij, and therefore to some maximal elements. Right? If it belongs to some gamma Sij, then by this inclusion partial order, it must belong to some maximal element, to some maximal gamma Sij or Ij in I star. Okay? And therefore P is a partition. So every point of gamma belongs to some gamma Sij. Therefore P is a partition. Okay? And all of these are nested or disjoint. And we've eliminated all the nested ones, right? So these are now disjoint elements which cover P. Okay? Because if any of these were to intersect, then one would be contained in the other, and therefore only one of the two will be maximum. So P is a disjoint partition of gamma. So P is a partition of gamma into pairwise disjoints. Sets, S sets, S subsets. Okay, and similarly, by the same argument, you can show that the set of unstable also is a partition into disjoint S subsets, U subsets. Okay, whose images are U subsets. Okay, and all we need to show now is that these are in fact the first return times. Okay, it turns out so we have a set of disjoint subsets, and they all map to U subsets. So we have almost what we need for the topological Young tower. We just combine all the S subsets with the same return time, and we get the level sets, as long as we show that these are actually first return times. So we need to show that now each of these must, all the points in here return for the first time at time I. Okay, so we need to show, we know that all these points return at time I, and they give a U subset. We need to show that that's the first return time. Okay, but that's very easy, and that exactly follows by this property of lemma 2. So suppose by contradiction, so to show that for all x in gamma Sij, that all x in gamma Sij have first return time tau of x equals I. Okay, so we suppose by contradiction, that so suppose by contradiction that there exists some J let me use the notation. Let me use the notation that I stated there. So let me, there exists some J between 0 and I, such that x is in gamma x ij. No, I'm using J again. No, so that's not good. Sorry. So let me call this K. Let me use the notation that I used there to state that. So let me call this KL. So to show that all x in gamma SKL have tau of x equals k. So if they in gamma SKL, then the first return time is equal to k. Suppose by contradiction that there exists some I strictly between 0 and k, such that x is in gamma SKL and fi of x belongs to gamma. Okay, then you can see immediately the contradiction is going to be. So we're exactly in the setting of that lemma. So if that was true, then this would imply Then by lemma 2, there exists some gamma Sij which contains gamma SKL. Okay? But this contradicts the fact that KL is an I star, contradicting the maximality of gamma SKM. I hope you can read. I realize the black was. Okay? So this is it. So those two lemmas, they imply the topological first return. We've constructed now the topological return Young power. We have one lemma that says that these sets that we've defined, these gamma Sijs, are S subsets and U subsets, and they map to each other, which is essential. That's the property that we want. And then we have a second lemma saying that they have this nested or disjointness property, okay, and just combining these two lemmas, we prove the theorem by taking the maximum elements and using that, showing that they must all have first, that you can find a disjoint cover, and that this must be actually the first return. Okay, so I don't have time to give a full proof of the lemma. We'll finish tomorrow, but first I want to give maybe an auxiliary lemma, which we will use in the next 10 minutes, which is where we use the nice property of the rectangle. So in the proof of lemma 2, let me leave the lemma 2 here maybe. Well, you know what? Maybe I think this is a better place to stop right here. So I think I'll stop right here and I'll finish tomorrow. This. Okay, Einstein. Clear problem. Andiamo a ri? Huh?
You didn't say that for the phone that they said. You said that they would buy automatic ticket for you. You didn't say? What is this email about? Which phone? You don't know.
Okay, I don't know. Bene, sono la mia sfida. Che lo sistema induzita, perché l'attore di là às vezes ele se refere senão quando as imagens às vezes de qualquer a maneira que você construi que você vai sempre estar induzido sono no retângulo un corollario nosso que tem a dinâmica simbólica, outro corollario nosso essencialmente também inclui a dinâmica simbólica, porque por causa do fato que a gente tem o primeiro retorno, então se você pega todas as imagens, você tem aqui esses elementos da partição e da partição, e você pega, que são S-subsets, você pega as imagens deles até que eles voltam, por causa do fato que esse primeiro retorno, todos esses subjuntos, as imagens todos os subjuntos, essencialmente isso dá uma partição clara. Porque você tem esse conjunto, a imagem dele é uma coisa assim, da mesma maneira isso vai para isso, vai para isso. Então isso dá uma partição de mapa. Lambda, conjunto hiperbólico.
Aí você não precisa se preocupar.
Não, não pode ser.
Porque
So ja się
Ma to solo non è tan diverso, la zampa che ci utilizza, io sono tema non sapemos se os tempos vão se integrar, apenas se movimento em torno, se uma medida invariante você não sabe que é.
Because always the trick is to have this slow down, but this slow down will
Mas se não for integrado,
be exponential.
os expoentes de Lyapunov,
So if you take a function, I think it's true, but if you take a function that vanishes at some
a
large order
hiperbolicidade que
derivative,
você tem na reduzida,
different,
quando você
you
agora
have exponential decay.
distribui essa hiperbolicidade ao longo das operadas, você obtém
But if you find like exponential case, so you have this between epsilon ball, when to take two epsilon balls, when the time to get from one ball to another is
porque você tem por
should
exemplo,
be
você
like
daqui
closer.
para cá tem uma certa
Okay.
expansão.
Good. But
And
then
therefore,
it's good.
but why? Because it seems to be with the
Agora, quando
the
você
time
bota
which is
dentro
to go
da
to the
conta
ball,
os tempos de prova, você tem que distribuir essa expansão.
Well, yes and no, because if you make the function to vanish at this point,
Yeah, a
you
function-
make you infinitely.
so if a function is vanishing to this point,
So
then
then it's the minus 1 over whatever.
so if it vanishes to some point, it's false. But
Quando você faz a média, você
Foi, infatti,
não consegue manter uma média não zero.
because some question is the system has a correlation, can it have zero?
Oh yeah. I was also trying to say. But yeah, because there the point is to.
But for example, if you want to show with characteristics substantial for each smooth map, you have for each smooth function theorem, when you don't need exponential relation, because you just, for example, you can take flow or something like this. In any case, your problem is not like, because in the actual problem, he also say that the system has, in addition, all the small constituencies. But in principle, it may be simply if you don't require.
Okay.
But on the other hand,
I see your point.
but on the other hand, also you also can put something like, for example, for Lorentz equations, you know, so
Quando você
No, these definitely produce several manifolds. Produce every one is so
but suppose you
if you guarantee some hyperbolic on the toes and then you fiber whatever fibering over the toes,
if you do something like which is, for example, if you assume the migration of the something
não, estamos terminando este
large,
não, estamos continuamos achando, reformulando, achando pequenas
no, what
coisas.
I think for instance can be done is any manifold times the torus has an exponential mixing. Probably it's hard, but probably it's doable.
I think that is possible. I think you can consider, basically you can show with these examples which will, like, if it's possible to show examples which will
Yes, exactly. But then you need to have this uniform hyperbolic basis. But in a sense it's almost yeah, I think it's more a question about the other question that you said. So it's, can you have a exponential decay with zero exponents. Because you will have some deletion of zero exponents in a sense. And whenever you have a function which has this non-zero differential on these points of zero exponent, and if you want to slow them down, zero exponents are introduce another measure.
But the point is that, yeah, of course, if all exponents are zero,
Yes.
but the problem is, the point is that you produce some examples which have some.
Okay, some non-zero exponent everywhere, but it may change from
Allora, nesse lemma che non troviamo. Nesse lemma dove non è se possiamo. Nesse modo che a gente
But I was thinking about examples such as the separation at least it gives you some kind of more
e por isso. Todo o resto essencialmente não sei. Agora não fiquei olhando Sim, sim. Bom, agora a gente precisa isso porque a gente tem que mostrar que bom, vai ver na prova que não pode a imagem do stable state não pode representar essa
porque é um momento que eu não vejo. Aí tem uns falam ainda, porque ainda essa parte aqui vem tudo, cara.
Sim, essa é fundamental. Mas a prova também não é difícil, mas não, a prova é fácil. Mas utiliza de maneira fundamental a propriedade vai dar esse mestre
Suppose that I'm going to distribution property. If I come down
Bom, primeiro não pode em nenhum ponto do caminho dele acercar isso, porque você sabe que no final ele é assim, se no meio do caminho é assim, isso significa que esse pedaço da variedade tal vai ficar no meio. E isso não pode, isso é exatamente a vantagem mais desse
Você falou aqui.
Não, esse aqui é o ponto periódico.
Sim. Tá.
E esse aqui é a variedade estável do ponto periódico.
Sim.
E a propriedade nice diz que essa variedade estável nunca é o sector interior desse. Essa é a propriedade nice. O ponto periódico não volta e nem pode voltar tão perto que esse aqui, que em princípio poderia voltar tão perto que esse aqui pode voltar assim. Isso não acontece. Agora, suponha que um stable state aqui, depois de um certo tempo ele volta para uma stable state. Agora, suponha por contradição no meio do caminho, ele faça isso. Então tem um pedaço dessa variedade estável no meio. Isso é no meio do caminho. Então depois, isso está no interior, quando volta deve estar, a imagem disso aqui deve estar aqui. Mas isso é proibido. Então isso não pode acontecer. Eu faço que isso não acontece, depois eu faço constar que eles não podem ter
No,
uma
a priori I see how to obtain
esse tempo aí, se eles têm uma
but exponential decay implies because what, for example, suppose you say your fiber is equal, then you can construct using accessibility easily some
Então é muito simples.
But the point is, with this company, let's suppose a function, when you don't want to tackle like at the distance, epsilon, but you can have anything which is epsilon or epsilon with 2 pi or
Okay. Now if I take an integer here, its opposite will be here. So the Lyapunov exponent of the guy here should be the opposite of the Lyapunov exponent here, because every element here is the inverse of an element here. Okay, but you also check it by looking at what happens when you cross this kernel. The first one comes from positive to negative, the second one remains positive, and the third one remains positive. Just keep on going, minus, minus plus, and minus plus. And you see the symmetry, and the symmetry comes exactly from the fact that every element here is the inverse of an element here. So the Lyapunov exponent here are the negative of the Lyapunov exponent. So each sign plus or minus is describing whether you have positive exponent or negative exponent along this direction. And as I said, so since Lyapunov exponents are not numbers, are functional, so expanding or contracting depends on which element of the action you are taking. Okay, let me just comment on the example I just draw. So you see that when you come into this chamber, you have 3 negative signs. So the 3 exponents are negative in this chamber. It means that there is an element of the action which has 3 of the numbers negative. And we saw the theorem last time that if this happens, then the measure is supported on a periodic orbit. Okay? So you can see from this picture whether your measure is already supported on a periodic orbit or if something else happens. And there is a way of giving examples of signs, so you can just play a little bit in such a way that none of these chambers become all negative or all positive. Okay, so these are the chambers. Let's keep the picture for a second in this 3-dimensional space. So if you go to 5 dimensions, typically you will have 5 lines here. You go into dimension 200, you have 200 lines if your time space is 2-dimensional. Then if you have time space dimension 13 and ambient space dimension 2000, you can imagine what will happen. These cones which have very high dimensional boundaries and did some combinatorial problems. Then really guess, I don't know, the intuition disappears and you really have to play a lot of combinatorial. So that's why it's better to remain dimension 3 and time space dimension 2. Simple picture. Okay, so now these are the chambers. Of course, options. Okay, so when you just come here and jump to this chamber, pick any element in this chamber, and you have 2 positive exponents and 1 negative exponent. As you have 2 positive and 1 negative, there will be an unstable manifold associated to these 2 positive exponents and 1 stable manifold associated to this guy. Okay? And since stable manifold and unstable manifolds are perfectly well determined and uniquely dynamically determined by the diffeomorphism, they will have to be invariant by all the elements of the action, not just by the particular element you are taking here. So it will be also invariant by all the others. Of course, may not be contracting or expanding for the other elements, but will be invariant by the other elements. So it is a very well-defined dynamical option. Okay? So, and the good news is that here I will have an unstable manifold tangent to the E2 plus E3 direction. The EU space here will be like that, while if I'm coming here, the EU direction will become E1 plus E2. Of course, the unstable depends on the element of the action I'm taking. Even though it's not, as I said, it's not really on the element of the action, it only depends on the very chamber. Okay, so in this picture you will have six very chambers, so you have 6 different possible unstable manifolds. So you have the unstable manifold for this guy, which is tangent to this guy, the unstable manifold for this guy, which is just tangent to the total space. Here is tangent to the first 2, here is tangent just to the first, here is empty, 0 space, and here is tangent to the last guy. So this gives you a huge amount of invariant subspaces which are very well dynamically determined. Okay? This is a very strong thing that we want to explore heavily. So let me just make some comment here, which relates with something that Yasha Besin said in his first lecture. So let's imagine you have just one diffeomorphism F. Okay? And you have this first diagonal of exponent, second, and so on. Assume the chi1 is larger than the chi2. Is larger than just one F. Okay, so the pacing theory tells you that there is an unstable manifold associated to these two directions, and there is a stable manifold associated to this direction. But it tells you more. It tells you that along this fastest direction, there is a strong and stable manifold, because it's the fastest. Okay? It's better to denote it in W1 than W. But there is no targeted invariant formulation. In general, you cannot give an invariant foliation associated to this intermediate type. And the reason is what Poletti said in the first lecture. The unstable is characterized by points that contract in the past. Okay? That's the way you characterize it. You have to go to the past to characterize this guy. Now, these guys here in the first direction are characterized by the fact that in the past they go the fastest possible to 0. So they go exponentially fast and very fast, along the chi1 direction. While the E2, if you want to determine E2, you have to go first to the past to make sure they contract, and then you have to go to the future back to make sure they contract less fast than this first direction. So you have to go to both directions to make sure this second guy exists. And the fact that you have to do this is what completely destroys the stable manifold theorem and the unstable manifold theorem, and you cannot put any proof to do that. So going to the past is reasonably nice because points stay together, but going to the future is bad because points tend to separate from you, and that's not good. Okay? So that's why in general, if you have only one diffeomorphism, then you cannot have this, or you may not have this second invariant submanifold. Now this picture completely changed in here. Okay, so let me draw a, a more reasonable Bayes chamber description here. So let's still do kernel Chi1, kernel Chi2, kernel Chi3. And now let's try to do something different. So I should do plus, minus plus. And then here I want n minus plus, I guess. So probably n minus plus, plus minus. So I have minus, minus plus. Then here I change the second guy. So what do I do for? Here I change the second guy, here I change the third guy, and here I have the opposite. And here I have the opposite of this, so it's plus, minus, minus, and here I have the opposite of this. Okay, so yes.
Can you say maybe the Lyapunov exponent for the 1 and 2 is equal?
Yeah, if they are equal, then you, in principle, you not even have this splitting. This is just a two-dimensional space, and you cannot split any longer. Okay? So, but the nice case is when you really have a simple spectrum, essentially, which is only one dimension. Okay, so let me just describe this picture for a second. So you have the first Bayes chamber here, let's call it the plus, and here is the opposite of this, we have a minus. There is a second Bayes chamber which has a plus, here is the second has a minus. Third Bayes chamber with a plus, and the opposite which has a minus. Then you have that for n in C1 plus, the unstable place of n is E3 for n in C1 minus, the unstable of n is E1 plus E2. Now if I do n in C2 plus, here n in C2 minus, I will have that the EU n is the E2 plus E3, and here the EU n is E1, and finally, if I take n in C2 in C3 plus EU n is E1 plus E2, or C3 plus is just E2. And when I have n in C3 minus, I have that EU n becomes just E1. So once I have this, once I have this, I get that the unstable manifold C1 plus, the unstable manifold of X with respect to this particular element of the action is tangent to okay? And similarly with all the other guys. Okay? And let me just now make a very specific case, which is, let's take n in C minus, and then I take n in C2 plus. So take n1 and take n2. Okay, then I get that for this guy, the unstable n1 of the point x is tangent to E, so it is C minus, so E1 plus E. And here I have the unstable manifold n2 of the point x is tangent to E2 plus C plus. Okay, so I have two invariant foliations, one which is tangent to E1 plus E3, and the other is tangent to E2 plus E3. And now I can intersect these two foliations. Okay? So this foliation has expanding property for N1, but is invariant by all elements of the action. And this has expanding property for N2, but is invariant for all elements of the action. Simply for other elements may do different things, but this invariant foliation. Now I intersect both. And what I get is a manifold which is tangent to the intersection of these two guys. The intersection of these two guys is the E3 direction. So this is tangent. Okay, so that way I can reach one direction without having it being the unstable or the fastest of n. Okay? So this gives me very important properties for this foliation, and this will be crucial in the theory. So that I can reach this intermediate even though I'm writing it as if it were E3. So there is no reason why it is the most contracted or more expanding in any sense. So it's just one intermediate foliation in principle. And I can reach it even though it's not the fastest, not the slowest, not the negative, not the positive. So just I can reach it by intersecting other guys. Okay? So this is not just an observation, it's the key observation that makes the whole difference between playing with only one diffeomorphism or playing with the group action. Okay, so it's this difference in the paradigm. So the center foliations here, the intermediate foliations, in principle do not exist, and even when they exist, are what is called not absolutely continuous. So it's very badly behaved foliation. While here, they exist, and the way you get them, they have very nice absolute continuity type of properties. So, and this makes the whole business. Okay, so let me stop for a second and let me show just two examples of the picture I just showed. One which is coming back to what we did, so it's two commutative matrices, A and B, in SLPC, So it's determinant 1, and they're analyzable, and without eigenvalues of modulus 1. It's not so hard, but not so trivial to find them. So you just play a little bit with characteristic polynomials and you find them. So then you have the eigenvalues, let's say positive eigenvalues. Values and commutative. And then essentially the very same game we did last time, we can do it now. So you can show you have a splitting of R3 as the sum of 3 eigendirections, and you have this lambda 1 of A, lambda 1 of B, lambda 2 of A, lambda 2 of B, and so on. Lambda 3 of A, lambda 3 of B, the eigendirections there, and you have this chi I of n1, n2, which is the logarithm of the lambda I of the A to the n1, B to the n2, which is nothing but n1 logarithm of lambda 1 of A plus n2 of lambda 1. Okay, so these are the Lyapunov exponents in this case, which is logarithm of the corresponding eigenvalue along this eigenvector. So this is oscillator decomposition, this is eigenvalue, and in this particular case, by a correct choice of A and B, you will have exactly this picture of the chapters. And you will see that just diagonalizing the matrices. Depending on where you choose your element of the action, you have the stable space being either one-dimensional or being two-dimensional. Okay, and the same for the unstables. Either one-dimensional or two-dimensional, and sometimes this E1 plus E2 is the unstable, sometimes it's this E2 plus E3, sometimes it's this E1 plus E3, I guess. Sometimes E1 plus E3. Okay? So it depends on what is your choice. You have this unstable being two-dimensional, and intersection of these two-dimensional gives you the one-dimensional. And the point is, let me just re-emphasize, so unstable manifolds are very nicely dynamically defined objects, and hence intersections of unstable manifolds is also a very nicely well-defined object. Okay, because it's intersection of unstables. We have intersection of nice objects, you get nice objects. If you need to make some argument of going back and forth, then you don't get an solution. Okay, so this is one example. Let me go to the second example. It will require a little bit more of near algebra. N is a quotient, so the manifold is a quotient of SL3R. Okay, so these are 3 by 3 matrices of determinant 1, and gamma is the lattice. Discrete or maybe not co-compact, but finite volume. So for my discussion now, really gamma is not playing huge role. So compact lattice. So you have such a lattice, and then you have it will be an R2 action instead of a C square action, but it's all the same. Have this group, call it A. This E to the D1, E to the D2, E to the D3. D1 plus D2 plus D3 equals to 0. So this is diagonal matrices with positive entries inside SL3R. And we have the action, natural action of A into diffeomorphisms of A. And the way it acts is you take your particular diagonal matrix, you apply it to the matrix A was already used. Times gamma, so B times gamma is an element of SL3R mod gamma, and the way it acts is just B times B times gamma. It's just left multiplication by this line. This is just a very standard type of group action, which is called the left multiplication. Div is a restriction of an action, so here is not just the group A which is acting, you have the whole SL3R acting. But I care about this sub action, which is when I restrict to this diagonal.
So D belongs to A.
D belongs to A. Yes, one has to be a little bit careful. So if it is the first time you see something like that, it's somewhat confusing the fact that the group that is acting and the manifold where you're acting are both in the same place. So then you have a matrix multiplying another matrix, but one of the matrices is the group acting and the other matrix is the space, the point in the space. So one has to be very careful of that. That is in a sense similar to what happens with rotation on the circle. Okay? So you have a point in the circle which is an angle, and you rotate it by an angle. So you just need to remember always who is the angle and who is the point. And of course, at some point you want to just forget about this and mix everything. Okay, so this group A is naturally isomorphic to R2. This is just the subspace of R3, which the sum of 3 coordinates is equal to 0, so this is just a subspace, the two-dimensional subspace, so this is R2. And you can apply Ocellet's theorem to this R2 action instead of the C square action. It's the very same Ocellet's theorem. Okay, and we will give you a splitting. So let's talk about dimensions first. So what's the dimension of M? Well, this is 3 by 3 matrix, so it's dimension 9, but I have determinant 1, so this gives me dimension 8. Okay, so I have an 8-dimensional space. Okay, now, Osseller's theorem, I can imagine that it will give me a split into 8 subspaces. And it does give you a split into 8 subspaces, but out of these 8 subspaces, you will have 2 directions which are isometric. So correspond to Lyapunov exponent 0 and even fully isometric. And this corresponds to the direction of the very same guy A. And that's the point of the A being simultaneously a subgroup and the group R. Okay, and the fact that this is an abelian group, it tells you that multiplying by this will not change the speed. It's like with a flow. When you have a flow, when you take the direction of the flow, along the flow there is no expansion, no contraction. Okay? So you always have one dimension of Lyapunov exponent 0 when you have a flow. Well, here you have a R square action, which is 2 commuting flows. And along this direction you will not have any expansion. Now you have 6 other dimensions, which will correspond to some Lyapunov split. So let me try to recognize this dimension. And instead of computing invariant subspaces, I will try to compute invariant submanifolds. So directly the foliations. Because then it's a matter of playing with groups versus Lie algebra. And I don't want to enter into the algebra, so it's groups are these are matrices, so it's much simpler to compute. So let me present some groups which are called the Rij groups, subgroups. So let me just start putting it this way. So the R1, 2, this is like you put once over there, or like, okay, now I just need to know what is. So the first is the row and the second is the column. So this is my first subgroup. The index 1, 2 comes from the fact that this is the first row and this is the second column. Okay, and the same way you will just build the, we put the plus here, and which is 1, 0, 3. And so on. Plus, which is accordingly the same, so you just put the t in the 2, 3 position, and then I have the ones below, so all these guys correspond to go above the diagonal, and now I have the ones that correspond below the diagonal, which will be the 2, 1, but then for the 2, 1 I will put a minus. You know, it's just notation to remind me something I have to say later. So with the 2, 1 is enough to know what's going on. So these 2, 1 will be this. And so on. Now you can just do some very trivial linear algebra computation, see that this is a subgroup isomorphic to the real numbers. Okay? So it's a subgroup. And I have 6 of them. And these correspond to 6 dimensions. And these 6 dimensions perpendicular, transverse to the flow direction, to the diagonal direction. Okay? And the tangent spaces to these will produce essentially the Ocellet space. Okay? And this is pretty much the same thing you do in the torus case. Okay? So in the torus case, you look at the splitting over the 0, which is a fixed point, is the identity element of the torus. You look at this splitting. This splitting indeed generates 1 parameter groups here, and then you translate these parameter groups over every point, and this gives you the foliation.
So, the sign, how do you decide with the plus or?
I will come in a second to that. So it's yes. So here you do exactly the same. So over the identity element, you have this group, which is a line, a curve, a one-dimensional curve. And then you can translate this one-dimensional curve to every other place in the manifold. Okay?
So I have a question. These 2 examples, maybe I can relate, but are there also some general existence theorems for these invariant
Okay.
manifolds in this case, or are these just all explicit examples?
These are explicit examples, so you can put all this into a complete general homogeneous setting where you have a Lie group G, a lattice in the group G, and then you have a subgroup, which is the acting subgroup, which there is A here is in square, say, which you take it inside of the affine subgroups of G essentially. And then since this subgroup of the affine subgroups of the affine elements of G, then it acts on the group G. So affine means just automorphism multiplied by the translation. So here the translation part is trivial because it's just automorphism. Here the automorphism part is trivial, it's just translation.
And the theorem says that that defines some...
That defines whenever you have an abelian subgroup here, that defines an abelian action, and you can recognize quite explicitly what are the eigendirections, what are the Lyapunov exponents in any of these situations. It's just some linear algebra style of computation. This is Lie group theory, so it's representation theory. That is a very explicit type of computation. So there is a lot of combinatorics where you can really make a very accurate description of what is exactly this the Lyapunov exponents for K. So it's fairly good, well understand theory. And of course, as with combinatorics, so in this picture I'm drawing, is low dimensions sort of combinatorics is something you can understand, but when you go to high dimensions, combinatorics starts getting not so pleasant. So it's okay, you go to the books and read it. Doing it by hand. Okay, so I have this. Now I have to tell you what are the Lyapunov exponents. So I told you that these are the Lyapunov subspaces. Now I'm going to tell you what are the Lyapunov exponents, so what are these functionals associated to these directions, and then we can clear why is the plus and the minus. Okay, so as I said, the time space is two-dimensional. Now the amount of eigendirections I have is, or Lyapunov subspaces is 6 plus the 2 which are isometric, so I will not count the isometric because this kernel is trivial, so it makes no sense. So I have 6 Lyapunov subspaces, so I'm supposed to have 6 Lyapunov exponents. Okay, so 6 Lyapunov functional. So in principle I will have 6, I guess it's 6 or maybe that's 5, but anyway. So I should have 6 lines there. But you will see that it will be only 3 lines, not 6. So let's compute what are the Lyapunov exponents. So I take this matrix here. Times gamma. Okay. So this is an element in this space. And I multiply by this matrix e to the t1, e to the t2, e to the t3. Which is the diagonal matrix. Okay. I just start to multiply these two matrices. So what's the outcome? Okay, this should give me e to the t1, e to the t2, e to the t3, 0, 0, 0. It will give me yet another couple of 0 here. And now this is the only position that gets some difference. So what will happen there? This will be multiplied by e to the t1 times, okay, just not to confuse the t's with the t1s, let's put an s. So this entry becomes multiplied by e to the t1. Okay? Times r. So this is where this guy is going, this one. Now I want to understand how these dynamics expand this direction. Okay, so the typical way you have to do it is take this infinitesimal and do the computation, but instead of taking anything infinitesimal, I will try to do it just on the picture. I have here, forget for a second about the gammas that I multiplied here. So I have here the identity element. I have here the whole curve, and I have here this R1, 2 plus of S, which is this matrix 1, S, 0, 1, 0, 0, 0, 0, 1. I have all these line, these one parameters are groups, so this piece of one parameter. Now I'm multiplying all this curve by this matrix here on the left. So this will move myself into this matrix here, e to the 1, e to the 2, e to the 3. And this will move me here into this other matrix. E to the 1, e to the 2, e to the 3. They have e to the 1 times s, 0. And so all this curve becomes this other curve. So that was what is going on here. And what I want to understand is, if this curve has some length, then I want to know what's the length of this curve here. Okay? Now, to understand the length of this second curve here, the best thing to do with computation is to take things back to the identity. Because computing things over the identity element is always the simplest thing to do. So you have to take things back to the identity element. And there is two ways of taking things back to the identity element. One is left multiplying by this matrix. So this will just undo what I just did. So that's not interesting at all. So I can right multiply by this matrix. If I right multiply by this matrix, then this point comes here. And then this curve will go to some curve around there. Which is this other curve? I don't know yet, so we will have to compute it, and we will see. Still, it seems like cheating, so why you are choosing to right or left multiply? So, because it will do the computation you want. Okay, so there is a reason why left, right here. And there is where gamma really started. Okay? So the whole issue here is that this is not an abelian group. Multiplying on the left or multiplying on the right is not the same thing. So this means that since this is not an abelian group, the distance function you are going to put there is not left and right invariant. It's not like in the torus. Okay, so the best you may hope in this case is to have a right invariant distance. So when you multiply on the right, it is an isometry. But then when you multiply on the left, it's not anymore an isometry. Or vice versa. You choose to be a left invariant distance, and then when you multiply on the right, it's not, and when you multiply on the left, it's zero. So the fact that I wrote things in this way, and I'm acting on the left, is because the distance I will be playing with is a right invariant distance, and that's why I'm acting on the left. And since the distance is right invariant, it means that when I multiply on the right here, the length will not change at all. But when I multiply on the left, the change will change. So that's why I'm multiplying on the left, it has some growth. To measure this growth, I multiply on the right, which will not change the length, and I can make my computation. Okay? So that's the game. So let's do this computation now. We multiply on the right. Here. By which is the inverse of the guys that move forward, and what I get is identity matrix here. I will get some curve and the other endpoint of the curve is just by multiplying this by this matrix. And I will just put the answer. You can check what is it. And the nice thing is that it will give me an element of the group I had. And this element is, we just write this entry here, is e to the t1 minus t2 times this. So that's the entry. So this parameter s gets multiplied by e to the t1 minus t2. Okay? And that's why it's called the 1, 2 also, not just because the position is the 1, 2 position, but it gets multiplied by e to the t1 minus t2. So in the ij position, you get multiplied by the ti minus tj position. Okay, so the fact that you get multiplied exactly by this number, you take logarithm, and that gives you what is the Lyapunov exponents. Okay, so you have these Lyapunov exponents. Lyapunov exponents. These are chi1 2 plus of t1, t2, t3, t1 minus t2, and you can check this linear function of chi, or in general, ij plus or minus. After all, the plus minus doesn't matter. This writing is the ti. And it's associated to the corresponding subspaces, which aij plus minus, which in general you write it as little r. ij, r comes from full space. You can here you don't put it. Okay. So far so good. So this is how you compute. Now let me tell you why the plus and the minus. So you see that the kernel of chi1, 2 is the same as the kernel of chi2, 1. Okay, because it's t1 equals to t2. Okay, when one is positive, the other one is negative. And this is why the plus minus I'm using. Okay, so I'm choosing, I'm making some choice, and I will be even more explicit in a second, of when I like this to be positive and when I like this to be negative. So the plus means that I like better this guy when t1 is larger than t2 than when t2 is larger than t1. This is a completely capricious choice, so you can choose the other way and you have the very same theory, so it doesn't matter. But it's that's where the plus and the minus. So you have here this very chamber picture. So each of the lines correspond to two kernels. So and then putting plus and minuses is a little bit complicated because well, you choose three of them and the others are the opposite. Okay? And let's say here is T1 larger than T2, larger than T3. You have to think of this R2 as being a subspace of R3. Okay? So then you have the three coordinates in R3, and in this subspace you have this picture. And you have this very specific base chamber, which again is some capricious choice, but it's a very favorite choice and it's a typical choice of very chamber. Okay? And the plus comes exactly from this. So from the fact that this is the favorite, which is when T1 is larger than T2, T2 is larger than T3. And these correspond to the plus I put are positive, and then the others are negative. And what is the reason of that? Is that I have yet another subgroup n, which is my n plus, which is this one is 3, such that So this is called the Heisenberg group, but it's a particular subgroup of SFVR, and this is nothing but the unstable manifold for T1, T2, T3, when T1 is larger than T2 is larger than T2 of the prime proportion. So this is the unstable manifold, and it's exactly the entries that appear when you want these three directions to be expanded. And that's why I put in the plan. And analogously, you have the n minus, which is the transpose of this. This one is 3 in R. And this is the stable manifold of T1, T2, T3 of the gamma. And for these guys, you do the other way. Then the same thing because it's the same. The upper triangulars are the unstable manifold, and the lower triangular is the stable manifold. Okay, for this very element I'm choosing here. Then when you start jumping from one Rayleigh chamber to another, then the stable manifold will change. So the typical case, for instance, is when you have something like this. It's not so trivial for me, but I should be able to put this. This, so this is 1, 2. What is this entry is 1, 3. And then 2, 3 is this guy. So if I did things correctly, no, this doesn't look very much of a group. So it's 2 is 2, 3 is second, and 3 is that, but no, it's not that the one I want. Probably what I want is 3, 2. Maybe I want this one. Yeah, maybe I want this one. Anyway, one has to make the complete picture, and if I do things correctly, this should be a subgroup. And then this subgroup corresponds to a very particular choice of T1 larger than T2 larger than T3, or whatever the base choice somewhere. Okay? Good. So this is another example of an action, and that's how you understand the hyperbolic splitting of these guys. Okay, very good. We have now invariant manifolds, this hyperbolic splitting. So let me move a little bit further. Define coarse Lyapunov. Okay, so we have our oscillated strip. Yeah, we have the Lyapunov directions. And we have this chi function which goes from Rk into R. Yeah, the action goes here from this. And you have the environment. Now, it may happen that two such spaces have Lyapunov exponents which are positively proportional. Okay, so what does it mean to be positively proportional? It means that they have the same kernel. This is the meaning of being proportional for two functionals. So if they have the same kernel, it's because one is the multiple of the other. And the fact that they are positively proportional means that the half space where one is positive is the same as the half space where the other is positive. So it's exactly the contrary to this picture. So there you have proportional spaces, but one is the negative of the other. So these are negatively proportional. So, but it may happen that they are positively proportional. And why this I want to distinguish this case is because this does not allow me to do the game I wanted to do before, which is intersecting unstable. Because if the two elements are positively proportional, whenever a vector there is expanded for one element, it will have to be, the other vector has to also be expanded because they are positively proportional. So I cannot pick an element which will expand this and contract this guy here, which means that either both are in the unstable or both are not in the unstable. I cannot distinguish them. I cannot separate them. And then I will enter into the problem of having one diffeomorphism. Okay? Where one is faster, the other is slower, or both are exactly the same, but there is no dynamical foliation. I can play with these two guys. And then I will not separate them. And this is what is called quartz-Lyapunov subspace. So, I have is the sum of all the j's, where chi j is c times chi I for some positive. Okay, so yeah, I'm just summing all Lyapunov subspaces whose Lyapunov exponents are proportional to a given one, chi I. And of course, this will be repeated, so if they are proportional, then I have some repetition in the value. But I'm just grouping them together. That's what I'm doing. So it's a quartz space, but still, it's better. And you can think of even the case of one diffeomorphism, one action, and what you are doing is taking the unstable space from one side and the stable space from the other. So you have several Lyapunov exponents, then when they are positively proportional, I mean, take the positive one and group them into one subspace, which is unstable, take the negative one and group them into the stable subspace. Okay, so that's what you do with just one diffeomorphism. Now you have a larger group action, you can make it finer, and this is the best finer decomposition you may play with. And then you have the theorem, which is essentially Pessin stable manifold theorem. Almost every x, there exists wi at x, a manifold, good manifold, tangent to pi hat such that alpha n of wi hat of x is equal to wi hat of x. I've already said. We have the right invariant property is tangent to the corresponding quartz-Lyapunov direction. And you have to think of this object as a better and more suitable type of foliation, like the unstable foliation or the stable foliation for the case of the time being one dimensional. In the examples above, these manifolds are exactly these one parameter groups like the ones we have. And in the case of the linear automorphisms of the torus, these are manifold are just the parallel of the eigendirection. Okay. So maybe let me give you one more example where you really have this type of business. So it's sort of a fake example, but you have these matrices A and B in SL3R, in SL3C, commuting. and you have the splitting and things. But now you may just play with an action which is like the following. So is in T6. So you have a to the n1 plus b to the n2, and here you have e to the 2 times n1, so 0, 0, and here you have e to the 2 times n1, e to the 2 times n2. Okay? So now you have, this is just a commuting action, C-square action, it's pretty much the same. You are just doing twice here than what you are doing here. And then you have different Lyapunov exponents, because the Lyapunov exponent in this direction is twice the Lyapunov exponent here, because I'm putting a square here. I could put 3 or I could put 1, so it doesn't matter. There is a square. But you cannot separate, so whenever this guy is expanding, this guy will be expanding and vice versa. So you cannot separate this horizontal with this vertical. Okay? And of course, this guy is linear, so you have very nice subfoliation, but things become very tricky. So that's the point. Okay. So now I want to play. Okay, but before that, since I was developing the whole theorem, I'm sure some of you are curious of why I'm doing all this. Okay, it looks very painful. So it was maybe fun at the beginning, but now it's starting to look painful. Okay, so let me take a couple of theorems you can prove by applying this, plus some entropy discussion I will do next time. Just state the theorem that I hope I will finish the proof of this theorem next time. Then I will start and state another theorem that I will not be able to cover them, but follow the same type of theory. Okay, and this theorem is sort of all given by Etienne and Bulger. So it's in the 90s. So let gamma in the lattice. Or you can take other groups here, but we are concentrating on SL3R, so let's just put SL3R there. And the lattice means discrete and finite volume quotient. So for example, for compact. And assume gamma acts on S1. Alpha from gamma diffeomorphism of the second. Then this way, alpha of gamma. It's essentially a trivial action. Okay, so the kernel is huge. This is huge. Assuming gamma is huge, meaning that this is a lattice, it should mean it is huge. Then the image is a finite image, so it means that the kernel is finite indexing gamma. So really, even though you are writing it as if it were an action of gamma, is not really an action of gamma, it's an action of a finite group, because that's what is the image. So other way of saying it is there is no really such an interesting action. Okay, and there is a more recent theorem by Aaron Brown, Sebastián Hurtado, David Fisher and Sebastian Hurtado. That says that the same is true in higher dimensions. So, but not the self-free. It says that if gamma is a lattice in SLNR, co-compact, and alpha from gamma into diffeomorphism of a d-dimensional manifold where d is at most n minus 2, so like 3 to 1, then alpha of gamma is fine. And this is very rigid, so this is maybe just here. Okay, so the proof I will present of this, give one of the key ingredients to this, then there is a second ingredient which really goes beyond the course. There is yet another theorem which one can prove using all these techniques. Which is even older than again this theorem. Which is Moore's normal sample theorem. This is 70s. Or maybe 60s. Late 60s or early 70s. And says the following. So, and gamma, I will just take it only in SL3R because any simple group will do the job. Or SNR. The problem SNR is not so hard. So SNR, a lattice. Yeah, let n be a normal sample. They're pretty much like the kernel of one of these alpha actions here. So it's a normal subgroup, and then what this thing is telling you is that then either n is finite, so the normal subgroup itself is finite, not just finite, it will be abelian, and in the center of the whole SLNR, so it's just plus minus identity. That's as it can be. Or gamma mod n is finite. It's almost. Okay, so if you look at what's the statement there, you can check that the possibilities where either this alpha is essentially 1-to-1 or it had infinite image. Okay, so what you have to rule out is the fact that this alpha being 1-to-1. This is not getting, so you assume it's 1-to-1 and you don't get anything nicer. So you really have to work very hard once it is 1-to-1, but still. So what is very nice of this theorem is that, as you can see, of course there is a legal structure here, but it's a purely algebraic theorem. So there is no dynamics at all here, just normal subgroups. And it's telling you some finite cardinality of normal subgroups. While the proof is 100% dynamics. It's exactly what we were playing 2 seconds ago. And so let me state the abstract dynamic theorem behind this theorem here. For this I need to add just one definition. So 2 definitions. I will just concentrate on SL3R, just to get ideas. So let me is A times n, so it's the n I defined before, and the a, so this is just upper triangular matrices. Equal to 1, equal to 2, equal to 3, S1, S2, S2, okay, and dIs and S1. So this is a subgroup of a self-reality, and this is called the Borel subgroup. So, no. One, we say Q inside SL3R is a parabolic subgroup. If P is a subgroup. So if Q is larger than P, then it's called a parabolic subgroup. And the good news is that P is on one hand a very large subgroup, and you can think of it dynamically. So it contains the dynamical, so the R2 orbits, the diagonal orbits, and it contains the unstable direction. Okay, so that's what it is. It's the unstable manifold with this orbit direction. Okay, so this tells you that it's very large. So the only thing that escapes to the parabolic group is the stable part. You really capture all the expanding part of the action. So this tells you it's very large, but on the other hand, among these large groups is the smallest. Because any other direction I will add to it, it will correspond to some stable direction. Okay? So this implies that you can fully characterize which are these groups Q. This will be very easy groups, so which correspond to adding numbers down here. So you can add this direction, or you can add this direction, or that's essentially all you can do. So if you add these two directions, then you get there. So you don't have that much manifolds. Okay? So you have essentially three possible groups Q, which are parabolic. Gamma be a lattice. Now, again, SL and R has the counterpart, and any simple group has, even semi-simple has counterpart here. So let gamma be a lattice. Assume gamma acts on space. X is just a measurable space. If you want, it's a topological space. And assume there exists H from SL3R. This is what I want. Have this quotient space. We'll discuss later what is this quotient space, but this is a quotient, so it's a group divided by another group. Okay? X. Just a map, a measurable map. So here I have Borel structure, here X is a topological space, so it's a compact metric space if you want, have Borel structure. Now let lambda be a measure equivalent to Lebesgue on P mod S. Okay, so this is a quotient of a group by a group, so it's a very nice manifold. Again, so if you think geometrically, what I said is P was essentially the unstable manifold with the diagonal direction. So when you quotient by this, what you are getting is a stable manifold, locally. So it's a three-dimensional space. Okay, and locally it corresponds to putting, what I put? Yes, this. Locally it corresponds to put zeros up here, ones in the diagonal, and putting numbers here. So that's what you are doing there. It's a three-dimensional manifold. You have a measure which is equivalent to the vector measure. Just call it lambda. There is a way of choosing a very nice measure there, but there is no need. Just this is the case. And consider the A star lambda. So you just push the measure to the other side. Okay. So let me warn you that the measure lambda, and that's why I'm just taking an equivalence, okay, will not be invariant by whatever action will appear here. Okay, so it will not be an invariant measure. There are no invariant measures for whatever I'm going to do here. So that gamma at on SLR on P by right multiplication. Okay, so I just call it rho of P times the matrix X, rho of gamma at P times X is P X gamma. So X is a matrix here, you just it's a natural action. And you will have, just as an observation here, rho gamma star lambda is equivalent to lambda but different from lambda. Okay, so I have then these two dynamics. I have these projective dynamics here, so these dynamics on this quotient space, and I have this abstract ergodic theory. And I have this map H which is just measurable, and I'm assuming that H composed rho gamma is alpha gamma composed H almost. And to say something there almost everywhere, I really need this equivalent here, and that this property here. That rho gamma star lambda be equivalent to lambda. Because if not, I can send a set of full measure to a set of zero measure, and it will be a disaster. Set of full measure. Okay. So you see it's a lot of hypotheses, but it's just measurable dynamics. Now comes the end. There exists Q, the parabolic group, and pi and capital H from X to Q mod X isomorphism. Okay, here by isomorphism means you put the measure mu here, you put again some Lebesgue measure here. This is an isomorphism of measure space, and it also does the commutative property here for the corresponding action. And it's really isomorphic, so it's not just a semi-conjugacy like here where you can collapse stuff. It's really a one-to-one map. So just to finish. That. is from our page and the diagram. So since Q is larger than P, there is a natural projection from here to here, and this is an isomorphism. This is the factor map. That's why it's called the factor theorem, because it's telling that whatever factor you have here, so you have the action of gamma here, the action of gamma here, the action of gamma here. So whatever factor of this guy, it has to be isolated. That's what it's telling. So whenever you have an abstract measure theoretic factor, it is indeed an algebraic factor in the measure category. Then there are some upgrades for the topological category and even for the smooth category, but then you have to put different types of factors. And that's what it's telling you, and it's a purely dynamical statement. Of course, the type of dynamics we start with is some algebraic style of dynamics, but I'm taking a completely measured theoretic abstract dynamics here, and I'm telling something about the structure of this. There is no dynamical action, no diagonal action here, there is no abelian action here in the statement, but the proof is about a diagonal action that will appear. Some Lyapunov exponents, which are the ones we already played. And Margulis' normal subgroup theorem restrict to understand this kind. This is a very straightforward reduction of Margulis' normal subgroup theorem to this statement here. Of course, this includes knowing what is property T, what is amenability, but these are standard knowledge. And then it's just this. So these three theorems I state, or maybe four, are what you can prove with this theorem I'm developing, but as I said, I only will be able to prove the first one. Okay, I think I should stop now. Not tomorrow, on Friday, I do the entropy and finish it.